Welcome to the first part of the nucleophilic substitution reaction at the saturated carbon atom. So in this lecture we will discuss about the reaction rate and the mechanism. Before going into the reaction, let us see what are the substrates that undergoes this nucleophilic substitution reaction. So alkyl halides are the common substrates that undergoes nucleophilic substitution reaction, and it ranges from primary to secondary to tertiary all the alkyl halides, as well as the allyl halides also undergoes the nucleophilic substitution reactions. Before going into the reaction, let us see some interesting facts. So we will see what can happen when we add water in alkyl halides. So if we shake some tertiary alkyl halide, for example in this case the tertiary butyl chloride with water, we will get the tertiary butanol. But can the same thing occur when we add water in a primary alkyl halide? No, the reaction will not occur. But we can achieve the goal by adding sodium hydroxide. So when we add sodium hydroxide in alkyl bromide, the primary bromide, we will get the alcohol product. And it is no need to mention that if we add sodium hydroxide in the first place, that is in tertiary butyl chloride, we will get the same result. So sodium hydroxide can do the job in both cases, but water can do the job only in case of tertiary chloride but not in case of primary alkyl halide. You just keep this thing in your mind. Now let us return to the structures of the substrates. So these are the substrates that undergoes nucleophilic substitution reactions. So what is the specialty in these substrates? If you look carefully and if you remember the concept of inductive effect, you will see that there is a charge separation in all these substrates, where the carbon atom which is attached to the alkyl halide or actually to the halide part is carrying a delta positive charge, that is a partial positive charge, and this thing makes this carbon center electrophilic, that is they are attracted towards electrons. And if you consider water or sodium hydroxide, they are called nucleophile. Why? Because they are having negative charge or lone pair of electrons and they are ready to attack on a positive center. So these two combine to give you the product. Now let us look into the rate of these reactions for the nucleophilic substitution reactions. So if we consider the first reaction, the reaction of tertiary alkyl halide with water, in this case the rate of the reaction is dependent only on the concentration of alkyl halide, and it is independent on the concentration of the nucleophile, that is either water or hydroxide. So this is a first order reaction. But for the second case, the reaction of primary halide, the reaction rate is dependent on both the concentration of alkyl halide as well as the concentration of the nucleophile, that is hydroxide. So it is a second order reaction. You just keep these two things in your mind while looking into the mechanism. Now considering these two facts, that the first one is the first order and the second one is the second order, we can propose a mechanism. Now if we look in the first case, it is saying that the reaction is dependent only on the concentration of alkyl halide. So that means the reaction cannot take place in a single step. It must be taking place in more than one steps, where the step on which the rate is dependent, that involves only the alkyl halide and not the nucleophile. So combining these two facts, we can propose a mechanism. What would be the mechanism? So first, this tertiary butyl chloride, it will lose its chlorine as a chloride, and that will give you this carbocation. Now this carbocation is quite stable. Why? Because it is stabilized by the plus I effect of all the methyl groups as well as the hyperconjugation of all these three methyl groups, and this thing is called intermediate. And the step is a slow step because you are breaking a bond, so it is a slow step. Now after formation of this carbocation, although it is stable, but it will be ready to be attacked by any nucleophile and you have hydroxide and your water molecules present in your reaction medium as nucleophile, so they will immediately attack on the carbocation to give you the product, and this step is a fast step. And you know that the slow step in any case will be the rate determining step, so the reaction rate will depend only on the concentration of alkyl halide in this case. Now considering all this fact, we can propose a name for this reaction. So N stands for nucleophilic because nucleophile is involved. S stands for substitution reaction because overall you are substituting a chlorine by a OH group, so that for that the S terms comes, and it is a first order reaction, so 1 comes, so it is called SN1 reaction or nucleophilic substitution reaction of first order. Now we have some questions. For example, why the OH minus is not directly attacking on the alkyl halide? Because we have seen that it is a polarized species, it already carrying a delta positive charge. So the question is why the OH minus is not directly making attack on the back side, and the reason is clear when you will see the structure in detail. So you can see the methyl groups, they are having all these hydrogen atoms, and this makes overall the thing quite bulky. So when the nucleophile approaches to attack at the back side, it will get a steric hindrance from all these methyl groups. So for this steric hindrance, the nucleophile cannot approach directly, right? So that's why it has to lose its chlorine atom first, and that will give you the carbocation. On that carbocation the nucleophile can easily attack. So the answer is clear now. So now we can look into the key points or key features of this mechanism. So the first point is it involves two steps. The step 1 is the formation of the carbocation, which is the rate determining step, and the step 2 is the attack of the nucleophile. The second point is the carbocation is planar, we have seen. The third point is the rate of the reaction is independent of the nucleophile and it depends only on the concentration of the alkyl halide. And the fourth point is the rate of the reaction depends on the ease of carbocation formation, that is the stability of the carbocation. And it is quite obvious because if the carbocation formation is not easy, then why it will form the carbocation? So that's the thing, and we will see all these points in detail in the following lectures. Now let us look into the mechanism for the second case, the second reaction. So in this case you have this primary alkyl halide, and on this primary alkyl halide, or in this case bromide, the hydroxide can directly make attack on the back side because it is already positively polarized. So the OH minus will attack over here and it will form this transition state. This is called transition state. Okay, so here you can see in the transition state the OH minus is entering and the bromine is leaving at the same time. So bromine is called leaving group, OH minus is called nucleophile. So here the entrance of the nucleophile and the leaving group departure is occurring at the same time. So that's why the reaction rate is dependent on both the alkyl halide as well as the concentration of the nucleophile. So by this single transition state you will get this alcohol product, and here we can propose the name. So N stands for nucleophilic, S stands for substitution, and because it is a second order reaction, so it is called SN2 reaction. Okay, and this transition state is very important. Transition state is a species which we cannot see in with our eye, but it is a proposed species which through which the reaction goes. Okay, so this is a single step reaction. Now the question is why in this case the carbocation formation is not occurring like the previous one. So what is the problem with this carbocation formation? You can see if the carbocation would form here, that would be a primary carbocation which is quite unstable, and that's why this carbocation formation does not occur. And it also doesn't need to form this carbocation because its backside of this CBr bond is not sterically hindered. It is quite free to attack by any nucleophile, right? So that's why here the carbocation is not forming. So what are the key points of this reaction? So it involves a single step where the attack of the nucleophile and the departure of the leaving group is occurring simultaneously through a transition state. Secondly, the rate of the reaction is dependent on both the nucleophile as well as the leaving group. Why it is so, we will see in the following lectures. And third point is the rate of the reaction is also dependent on the stability of the transition state. So here the carbocation is not involved, but the rate of the reaction is dependent on the stability of the transition state, how easily the transition state is formed or or how lower the energy of the transition state is. And in the following lectures we will discuss all these points. Namely, in the next lecture we will discuss about the effect of solvent as well as the effect of structure on the rate of SN1 and SN2 reactions. So for that, subscribe this channel, and thank you for watching. Have a good day.